Let's look at the 4 types of chemical reactions using the classification system most often used in colleges today. They are called simple decomposition, acid-base, precipitation, and oxidation-reduction, which is frequently shortened to redox. There may be other types of reactions, but this covers 99% of what you will see. First, simple decomposition. Sometimes a compound, and it pretty much is always heated, just breaks apart into 2 other molecules or even an element in a molecule without the exchange of ions or the movement of electrons. This does not often happen. The most common example is the dehydration of a hydrated salt. So for instance, copper sulfate pentahydrate, when heated, will break up into copper sulfate anhydrous and 5 moles of water per mole of the hydrated salt. Many other hydrates will break up like this as well, and this one is often used as a simple stoichiometry introduction in a high school lab. The second type we will call ion swaps, and it actually encompasses 2 classes of reactions. An ion swap involves the exchange of anion and cation between 2 compounds in the reaction. Some texts call this double replacement or double displacement, and that's a term that was used many years ago, and it's a little bit misleading. In this case, we're just generalizing and saying compound AB reacts with compound CD. The ions swap, no electrons are exchanged, and the products are AD and CB. There are 2 types of ion swaps that we will study. The first is the acid-base reaction, and the second is the precipitation reaction. Both are ion swaps. Acid-base reactions. We'll use the Bronsted-Lowry definition in that acids donate protons, bases accept protons. For example, sulfuric acid here reacts with 2 moles of sodium hydroxide to form 2 moles of water and 1 mole of sodium sulfate. And if all this is done in water, the acid and the base, were in water solution to begin with. The sodium and sulfate ions are in solution in the end, but water is formed, and water does not break up very much at all into ions. The net ionic equation says that 2 moles of hydrogen ions react with 2 moles of oxygen ions, hydroxide ions, to form 2 moles of water. And of course, the better way to say it is just H plus OH minus reacts to form H2O liquid. But there are other acid-base reactions, and that is because bases can accept protons even if they are not hydroxide ions. In this case, hydrochloric acid will react with sodium cyanide to form the lethal gas hydrogen cyanide and sodium chloride. Again, these are all ions in solution. The gas, however, would bubble off. Cyanide ion is acting as a proton acceptor here. Precipitation reactions. In this type of ion swap, you have 2 ionic substances, usually salts, and they swap ions, but one of the products, the ions are bound up so tightly together that water is unable to break it up, and so it falls out of solution as a precipitate or solid. In this case, aqueous AB and aqueous CD react to form solid AD and aqueous CB. For example, one that is often used as a demonstration, lead nitrate solution reacts with sodium iodide solution to form the yellow precipitate lead iodide and aqueous sodium nitrate solution. In rare cases, we could have both ions swapping and both precipitation and acid-base reactions occurring at the same time. Perhaps the most famous of these, lead hydroxide, reacts with sulfuric acid, and it forms lead sulfate and water. So it's reacting to form a precipitate, and since it's forming water with a hydrogen ion swap, we have an acid-base reaction. Barium hydroxide and sulfuric acid do the same thing. The final class, and this is a new type of reaction, different from an ion swap, is the oxidation reduction. There may be the most important, since almost every reaction in your body is a redox reaction. We literally cannot live without oxidation reduction. But to stay with the inorganic, electrons are transferred, and whether it's organic or not, from the oxidized substance to the reduced substance. This is an oxidation. Iron, solid iron, is losing electrons and forming aqueous iron 2+, or the so-called ferrous ion. In this reduction, which could happen at the same time, silver ions are reduced to silver metal. In this case, of course, we'd need this to happen twice. We'd need 2 moles of silver ions to capture the electrons given off by just 1 mole of iron as it oxidizes. How to recognize redox reactions? There are several ways to look, even if you don't know that electrons are being transferred. If the charges on an ion change in the course of the reaction, it's a redox. Iron 3+ becomes iron 2+, you wouldn't even need to see the electrons. If you've got this on one side and this on the other, you know an electron has been gained or lost. If an element appears without a charge on one side and with a charge on the other, well, it's either gained or lost electrons. So in this case, copper is losing 2 electrons to become copper ions. You see the copper on one side with no charge, and the copper ion on the other side with a charge. You know it's a redox. Magnesium and gold ions will react to form magnesium ions and gold. This is not a balanced equation, but you can see we've got here a 0 charge and here a 2+. It had to be an oxidation. And this 3+ going to no charge is obviously a reduction. And finally, if an element appears on one side and a compound of the element appears on the other, it's a redox reaction. So for instance, all reactions with oxygen gas are going to be oxidation reductions. That was the original definition of an oxidation. And finally, of course, as we said previously, if it's a biological reaction, it's a good guess that you've got an oxidation reduction.